modern wireless communication system at Department of Physics Information Technology, New Delhi, also at DST UGC. Sir is currently working as director at Center for Development of Physics Education, additional director at Center for Converging Technology, course, coordinator at DTC program of MHARD, New Delhi. Now he is going to enlighten us on topic vacuum tube type conventional microwave sources. Sir, you can start your session.
Okay, thank you for inviting me. So good morning to all of you. My topic is vacuum tubes type conventional microwave sources. It covers introduction of solid state devices based amplifier and oscillators, limitations of conventional active device based amplifier and oscillators at microwave frequencies, working of conventional microwave sources, two cavity klystron, reflex klystron, then experimental part on reflex klystron, and then working of magnetron if time will allow us. So first of all, we will discuss how do a solid state device based amplifier and oscillators work. As you know, there are some active devices like transistors, ICs, which work as a amplifier and oscillators. In amplifier and oscillators, we connect a DC power source with an active device, and then we apply a small AC power signal. Then this active device mix some DC power to the AC power, and then we will get amplified AC output power. So DC power is essential for amplification as well as for oscillators. So suppose 1 milliwatt power is given to this active device, then 9 milliwatt power is mixed by this active device from the battery, and we will get 10 milliwatt output power. Therefore, gain of the oscillator is amplifier is 10. In oscillator, we use a tank circuit, LC circuit. In tank circuit, an inductance and capacitance are connected, which produce oscillations of electric charges, and this oscillation of electric charges produce electromagnetic waves which are extracted in external circuit. Suppose this LC circuit is having 10 milliwatt power, then 9 milliwatt power we can extract, and then 1 milliwatt power is fed to the input of an active device, which mix DC power, and then it becomes 10 milliwatt, and then this 10 milliwatt power is feedback to the tank circuit, LC circuit, by some feedback network. So this feedback network is important, and as you know, this feedback must be positive feedback. What does it mean? It means the charge carriers which transfer power from output to the tank circuit should interact with this RF field of the AC circuit so that it can transfer power to the tank circuit. There are two modes. In positive half cycle, if electron interact, then electron extract energy from the LC circuit. But if in negative half cycle, electron interact with the tank circuit, then electron transfer to the power to the tank circuit. So this is the important conditions which should be maintained in each amplifier or oscillator. Now at microwave frequencies, there are some limitations. We cannot use this ordinary oscillators and amplifier at microwave frequencies. This is the basic oscillator circuit.
Excuse me, sir. Sir, are you sharing the slides?
Just
Sir, they are not visible.
now it is. Are you getting it?
Sorry, sir.
आ रही है क्या पावर?
No, sir, we can't.
लाइट दिख रही है नहीं दिख रही अभी? शेयर हो गई क्या? शेयर हो गई अब?
Yes, sir, it is visible now.
Yes, sir, it's visible now. Yes, sir, it's visible now. You can start, sir.
So this is the amplifier and this is the oscillator, which are based on conventional active devices. So what I have told you, that some output power is feedback to the tank circuit. So basic oscillatory circuit is tank circuit, which is used to produce electromagnetic radiations, and frequency is decided by this f is equal to 1 upon 2 pi under root LC. Why we cannot use LC circuit at microwave frequency? At microwave frequencies, we need inductance of the order of 10 to power minus 9 to 10 to power minus 11 Henry and capacitance of the order of 10 to power minus 9 to 10 to power minus 11 farad, which is very, very small, tiny devices. So it cannot handle the power as well as the lead inductances of the conducting material which is used to connect the device is not possible. So suppose if we connect wires from output to input, then it will take some time for charge carrier to transfer power from output to the input. In that case, it is difficult to maintain the conditions in which the interaction takes place in retarding mode. In oscillator, as the charge carriers transfer output power to the tank circuit, and the time taken by the charge carriers from output to the input is of the order of 10 to the power minus 6 to 10 to the power minus 8 seconds. During this time interval, at high frequency, the field in the tank circuit changes so many times. At low frequency, the field remains constant when electron interact from output to input, and we can maintain the condition of positive feedback. But at high frequency, the field of this tank circuit changes rapidly, and therefore it is difficult to maintain the positive feedback conditions for every cycle. So it is difficult to obtain the microwave by using conventional circuits. So what we do, we design cavities. As you might have read, that cavity is a kind of tank circuit whose inductance and capacitance is very small. So if two plates are shorted by conducting wires, then it becomes cavity. So this is the equivalent circuit of capacitor, and when it is shorted by conducting material, then it becomes a tank circuit whose frequency is of the order of 10 to the power minus 9 to 10 to the power minus 10 to the power 9 to 10 to the power 11 hertz. So we can design C and L so small by using a large volume of conducting material so that it can handle the power, it can maintain the oscillations. Now this is the fundamental interaction part in tank circuit of this cavity. Suppose this cavity is having field which is along the direction of motion of electron. Means right plate is positive, left plate is negative. When an electron enter in this region, then the force on this electron is such that the electron slows down. And in this case, the electron velocity increases when it moves from negative plate to the positive plate. This is the basic interaction in the cavity. तो अगर ये हम देखो इसमें आप RF फील्ड अगर हम अप्लाई कर रहे हैं तो राइट प्लेट और लेफ्ट प्लेट की पोलरिटी कंटिन्यूसली चेंज होती जाएगी. मीन्स ड्यूरिंग पॉजिटिव हाफ साइकिल the electrons are accelerating mode, and during negative half cycle the electron is in retarding mode, and when there is a zero field then there is no change in the velocity. So this is the basic interaction of electron in the cavity. So this type of cavities are used. These are called Re-Entrained type cavities. Means the walls of the cavity at the center is very narrow, so that interaction time is very small. So this is the rectangular re-entrained cavity, and this is cylindrical re-entrained cavity. So these are two grids G1 and G2. Between these two grids, the RF field and इलेक्ट्रॉन बीम इंटरेक्ट इन द कैविटी। जैसा टैंक सर्किट के अंदर आरएफ फील्ड और इलेक्ट्रॉन्स के अंदर इंटरेक्शन होता है और पॉजिटिव फीडबैक में पावर ट्रांसफर होती है। सिमिलरली इन दिस केस द आरएफ फील्ड generated in the cavity which interact with the electron beam in 3 modes. As a result, we'll get output power. What we have to do? Suppose electron enter in this gap for a small duration, and during that duration the field is in accelerating mode, then electron acquire the energy from the cavity. And if it is in the retarding mode, then power is transferred from electron to the cavity. So this is the basic phenomena which takes place in the klystron. Now this is the construction of a 2-cavity klystron. We are having a electron gun, anode, buncher cavity, and catcher cavity, and then collector. You might have read in theory as well as in practical classes the construction of klystron. So electrons are generated, produced by this electron gun. This is indirectly heated cathode. When cathode is heated, electrons are emitted from the cathode, and these electrons are accelerated by an accelerating potential V0. This is the basic phenomena by which we transfer energy from a DC source to the electron.
Are you?
So these electrons are uniformly accelerated by DC field, means velocity of all the electrons are equal. And when these electrons passes through this anode, we will get a pencil like a beam of electron which interact with the cavity. So this is the first jerk which this cavity experienced by these charge carriers, and an RF field is generated inside the cavity. So we know do not apply any external RF field or AC field from external source. Due to this interaction of electron beam and cavity, an RF field is generated inside the cavity, and the frequency of that field is decided by the dimension or volume of the cavity. So we keep the dimensions of this cavity or volume of this cavity is designed in such a way that we get the desired frequency. Suppose we have to design cavity for 10 to the power 9 gigahertz, 10 to the power 9 hertz, or means 1 gigahertz. Then dimension is suppose or volume is V1, and if we have to design for 10 to the power 11 hertz, then we have to reduce the dimension. So frequency is inversely proportional to the volume of the cavity. So the RF field is produced due to this electron bunch, and this is called perturbation method of cavity excitation. Once the RF field is generated, the polarity of these grids continuously changes after half cycle, and then the electron beam interact with this RF field, and we need a small time period during which this interaction takes place. अब मैं एक एग्जांपल आपको देता हूं. सपोज यहां से 100 इलेक्ट्रॉन्स यूनिफॉर्म वेलोसिटी के अंदर इसमें एंटर कर रहे हैं। 100 इलेक्ट्रॉन्स अगर यूनिफॉर्म वेलोसिटी से इस रीजन के अंदर आएंगे और वापस केविटी के अंदर साथ इंटरेक्ट करेंगे तो 50 इलेक्ट्रॉन्स तो पॉजिटिव हाफ साइकिल में इंटरेक्ट करेंगे और 50 इलेक्ट्रॉन्स नेगेटिव हाफ साइकिल में इंटरेक्ट करेंगे। नेट रिजल्ट क्या होगा? जितनी पावर इलेक्ट्रॉन से केविटी को ट्रांसफर होगी उतनी पावर वापस इलेक्ट्रॉन्स केविटी से ले लेंगे। नेट ट्रांसफॉर्मेशन इज 0 and we do not get any RF field. So what we have to do? We have to divide these 100 electrons in two parts. There are some region where electron density should be high, and these high density electron interact in retarding mode so that large number of electron can transfer energy to the cavity, and very small density of electron region interact the cavity in positive half cycle so that net transfer energy is from electron beam to the cavity. That's why we need velocity modulation. So the basic principle of Klystron is based on velocity modulation, density modulation, and then formation of bunches, and that bunches should interact to the RF field in such a way that densely region interact in retarding mode. So our next suppose this is the RF field of the cavity. If electron interact at this point, the velocity of electron increases V0 plus delta V0. So uniformly accelerated electrons from the electron gun when interact with this RF field, then velocity at this point is V0 plus delta V0. So those electrons which enter the cavity at this point, the velocity of those electrons becomes V0 plus delta V0, and those electrons which enter the cavity at this point, then the velocity remains unchanged V0, and those electrons whose velocity which enter at this point, then velocity reduces to V0 minus delta V0. And similarly, we will get so many electrons with different velocities. Therefore, this process is known as velocity modulation. The variation of velocity of the electrons due to interaction of the RF field is known as velocity modulation. And this velocity modulated electrons enters in the drift space. This is called drift space. And in two cavity klystron, this drift space is field free. There is no electric field in this region. Therefore, these electrons move without any change in velocity in this towards this cavity. So there are some electrons which leave the buncher cavity earlier with slow velocity, and then next electron move with high velocity. So this electron may catch the electron which left the cavity earlier, and the region means suppose electrons at this point leave the cavity at this point with slow velocity, then V0 velocity and V0 plus delta V0 velocity. So slow electrons are followed by fast electron from point 2 to point 3. So these electrons come closer because of variation in velocity. If we consider this part, means this electron move earlier with high velocity, and these electrons follow with slow velocity. So these electrons cannot catch this electron. So at some places in the drift space, the electrons come closer and form high density regions. And at some places, electrons are lightly dense and bunches are formed in the drift space due to velocity modulation. So suppose 100 electrons are entering in the drift space, then 80 to 90 electrons come closer and form highly dense region, and rest 10 to 20 electrons spread in larger region. When this density modulated beam enter the catcher cavity, then we have to adjust the field in such a way that this densely populated beam should enter the cavity when the field of the cavity is retarding mode. Means this is the center of densely modulated beam bunch. When this bunch enter the cavity at this point, the field is retarding field. Therefore, electron transfer the energy to the cavity. Means this difference should be 3 by 4 of time period of the RF field. Then only these electrons can transfer the energy to the cavity. Maximum energy is transferred when this time is maintained, or this should come. These should come at this point. This is also a second point. If field is small, then it will take more time, and this center of bunch of electron interact the second cavity at this point. So this is the second mode. Similarly, we will get so many modes. The first mode means time period from denser electron to interact at this point or this point. So this is the mechanism of the klystron. Now this is the construction of reflex klystron, in which same we have a electron gun, anode, and a single cavity which act as a buncher as well as catcher cavity, and then there is a reflector. Now we apply a negative potential at this reflector. So this is the drift space. The phenomena from electron gun to buncher cavity is the same, but there is a change. We apply a negative potential between this cavity and reflector, and due to this reflector voltage, electron enter in a drift space which is having negative field. So there is a difference. In two cavity klystron, the drift space was field free, and in reflex klystron, this drift space is having negative potential. So the electron enter the drift space with velocity modulated electron enters the drift space, and then due to this negative potential, these electrons reflect back. So there is a change in phenomena due to this negative potential or negative field of the, so those electrons which are having more velocity, they will penetrate more distance in the drift space, and those electrons which are having less velocity, they are reflected back earlier. So there is a difference in the bunch center, and the same cavity is used as a buncher cavity, means for the velocity modulation, and catcher cavity means to extract the power from the electron, the same cavity. But during the motion from right, left to right, this first grid is at negative potential, and at the same time this second grid is at positive potential. But when electron reflect back, the field at this cavity grid is positive and this is negative, but the RF field which we have plotted is of this grid, first grid. So we are plotting RF field for the first grid. So when electron enter in the cavity, the polarity of the field is different from the electrons which enter the cavity from the drift space to the cavity. So this is the difference. Means in reflex klystron, we should have interaction in such a way that the electrons with higher velocity enter the drift space earlier and travel more distance. And then the electrons which enter the cavity later should have less velocity so that they come earlier. So from point 1 to point 2, they form high density region. In contrast to two cavity klystron, in which the electrons from less velocity to high velocity form the density regions. So bunches are from point 1 to point 2, means bunch center is at A. Now this center of bunch should enter the cavity at this point. Means at this point it appears that it is in accelerating mode, but actually this is the field of left grid and the bunch are facing right grid. So when left grid is at positive potential, the right grid is at negative potential. So at this instant of time, means from time 3/4 of time period, the density, high density bunch should enter the cavity at this point. Means after a 3/4 time period, or 1 plus 3/4 time period, means at this instant, so that the more electrons can transfer energy to the cavity, and this energy is extracted by a loop conductor to the waveguide. So in a flux klystron, the electrons, after traveling the drift space and reflecting back to the cavity, the energy is transferred to the cavity. So when we change the reflecting voltage, reflector voltage, the time period will change, transit time will change, and at certain time, depending upon the reflector voltage, we are able to maintain a condition in which the electrons can transfer energy to the cavity. Otherwise, the power is zero. So when you perform the experiment, you have to change this reflector voltage such that we'll get maximum power output. Means at this instant, the highly dense electron interact the cavity in retarding mode and will get output. Otherwise, the electron interact with the cavity in accelerating mode and power is extracted by the electron from the cavity and this electron get hit up and it may burnt out. So we have to careful about this condition. Now this is the block diagram of the experiment which we perform in lab. Klystron power supply, Klystron with Klystron mount and tuner, isolator, attenuator, detector, and at the last power meter or indicating meter. So here it is Klystron power supply. This Klystron power supply, as you have already read about that, it is used to energize the Klystron in proper mode. Means first we apply maximum reflector voltage, means of the order of 240 volt, and then we increase the beam voltage up to 300 volt, and then we will reduce the reflecting voltage to get the desired modes in the Klystron. So there is a device called Klystron mount, and this Klystron mount is having a plunger like this, and this plunger is used to match the impedance of this Klystron with the waveguide. So when you perform experiment, be sure that the impedance of the Klystron mounted in the mount at a point should be equal to the impedance of the waveguide at this point. So by varying the position of the plunger in the Klystron mount, we can match the impedance of Klystron and impedance of the Klystron mount so that maximum power may be transferred from Klystron to the Klystron mount. And then this power propagate through the waveguide towards right. And here is the detector. And this detector is consisting of a crystal diode which converts RF field into DC power. And this DC power is measured by the indicating meter, or we can directly measure the power at this point if you are having power meter. And this deflection is proportional to the input power, because this diode convert the RF power into DC power, which is proportional to the input power. And this is the frequency meter, direct reading frequency meter. The working of this frequency meter is that we have placed this frequency meter in the path of RF field. Means microwave power is traveling from Klystron to the detector, and there is a waveguide and a tuner. Means a cavity is fixed in this frequency meter, and this coupling is through a hole. There is a hole in the bottom of this cavity, and this hole is connected to the waveguide. If we change or rotate the frequency meter, then frequency of this cavity changes due to change in volume of the cavity. At a certain frequency, the frequency of this cavity is equal to the frequency of the microwave which are traveling from Klystron to the detector. At this point, the maximum power is absorbed by this cavity. Suppose 1 milliwatt power is propagating from left to right. We are getting 100 division deflection. When this cavity is matched with the impedance of the waveguide or frequency of this cavity is equal to the frequency of the microwave, then power enters in the cavity. Power is absorbed by the cavity due to resonance, and we will get less power in the detector, and there is a dip. There is a minima in the deflection meter. So this frequency is directly read over this scale. There is a vertical red line and two horizontal red line due to and this vertical line between this two horizontal line indicate direct frequency. So in Klystron experiment, we have to measure frequency at every point where we are getting power. So this is the indicating meter. This is the frequency meter. Now what we do? This is the experimental steps. Map the reflector voltage to a maximum 240 volt. Increase the beam voltage up to 300 volt. This is the basic conditions for each experiment where we use Klystron. First, make the beam voltage maximum so that electron reflect back from the reflector. Otherwise, the electrons strike with the reflector and they can damage the reflector. So apply the maximum negative potential and then increase the beam voltage up to 300 volt. And by gradually decreasing the reflector voltage, we can observe different mode of oscillations. So reduce the reflector voltage in steps and note down the output power or the corresponding deflection in the indicating meter, which is proportional to the power output. Means there are two sources to detect the power. First, if you are having power meter, then we can directly measure the power. If we generally we do not have power meter because it is expensive, so we are having a detector, microwave detector, in which a crystal diode is there which converts power into DC power, and that DC power or DC indication in a current is proportional to the output power of the crystal. So by observing the deflection in terms of number of divisions, it is not the power, it is the number of divisions on indicating meter, which we can note down. And at each point where we are getting power, we have to measure frequency. Suppose we start from 240 volt, we do not get any power because the interaction is not favorable. At 170 volt, suppose we get 20 division on indicating meter. So this is the starting of the formation of the bunches and interaction with cavity in favorable mode. जो हमने कहा था कि इलेक्ट्रॉन की जो बंचेज बन रही हैं उनको रिटार्डिंग मोड के अंदर इंटरेक्शन करना है, वो इस पॉइंट से स्टार्ट होगा. So this is the first point where we will get power output. And even at this point, not all the electrons transfer power to the cavity. Only a few electrons which are more than the accelerating mode. But still, suppose 100 में से 50-60 इलेक्ट्रॉन्स ही यहाँ पर पावर केविटी को ट्रांसफर कर रहे हैं, तो 20 डिवीजन आउटपुट आएगा. सो the interaction in favorable mode start from 170 volt, and as reflector voltage increases, the more and more electrons interact with the cavity in retarding mode and will get more power. So the maxima occurs suppose at 166 volt and the maximum deflection is 80 divisions. So the pattern is like this. From 170 to 166, we'll get 20, 60, 80, 50, 30. And at every voltage, we have to obtain the frequency. There is a variation in frequency due to reflecting voltage. And we'll get different frequencies at different reflector voltage. So by using direct reading frequency meter or other frequency meter, we have to measure frequency at every beam voltage where we are getting power. And after 166 volt, if we reduce the reflecting voltage, the power once again reduces to 0. And then from 170 to suppose 158, we are getting power output like this. And then from 158 to 110, again the power is 0 because the interaction is in not our favorable mode. And then from 110 volt, if we reduce the reflecting voltage, then once again we'll get second mode, means we'll get favorable interaction, and this power is varied from a certain minimum value to a maximum value and then reduces to 0. So this is the second mode. This is the first mode, means the interaction is near about 3 by 4 second. T, capital T means time period, 3 by 4 of time period of the RF field, and this is 1 plus 3 by 4 of time period, and this is 2 plus 3 by 4 of time period, or any integral multiple of these. So if we plot output power versus repeller voltage, we will get the curve like this. And similarly, if we plot frequency versus repeller voltage, then we'll get the curve like this. These are called frequency versus repeller voltage curve, and these are the characteristic curve of reflector voltage. Now we can calculate mode number, means suppose the first maxima is at V2 voltage, the V1 voltage, and second maxima is at V2 voltage. Then by using this formula, n plus 3 by 4 upon n plus 1 3 by 4 is equal to V2 upon V1, where n is any number. By solving, means we are having this repeller voltage and this repeller voltage corresponding to maximas, and then by ratio of these two maximas, and this by using this formula we can find n, and this n may be 1, 2, 3, 4, any integral, approximate integral. Suppose we are getting small n is equal to 0.8, it means n is equal to 1. If we are having n is equal to 1.75, it means small n is equal to 2. So these are the mode numbers we can obtain. Similarly, we can find electronic tuning sensitivity. In practical, you have to measure ETS. So what is ETS? There are two types of tuning: mechanical tuning and electronic tuning. Tuning means variation in frequency of the microwave generated by the klystron. We can vary the frequency from, suppose in X band, we can vary the frequency from 8.22 12.4 gigahertz. So by changing the dimension of the cavity, we can change the frequency of the RF field. Means by changing the volume of the cavity by using a screw mounted on the top of the klystron, we can vary the volume of the cavity and then we can change the frequency of the klystron, and this is known as mechanical tuning. So by mechanical tuning, we can change the frequency from 8.2 to 12.4 gigahertz, near about 2 gigahertz variation in the frequency. This is called mechanical. And the second part is electronic tuning. Electronic tuning means the variation in frequency of the RF field due to repeller voltage. So by changing the repeller voltage, the interaction of electron beam with the cavity change the values of L and C of the cavity. As we know that L cavity is equivalent to an LC circuit, and for a fixed volume, L and C is fixed, but by interaction of this electrons due to repeller voltage, the impedance or the parameter L and C of the cavity changes. And this change is very small. We can change the frequency by repeller voltage of the order of in the order of only 500 megahertz. So by mechanical tuning, we can change the frequency from 12.4 to 8.4 gigahertz. But by mechanical tuning, by electronic tuning, we can change the frequency by a small amount, means of the order of 500 megahertz maximum. So this is the electronic tuning sensitivity. So electronic tuning sensitivity is defined as F2 minus F1 upon V2 minus V1. Means frequency F2 corresponding to repeller voltage F2 minus frequency corresponding to repeller voltage V1 divided by change in potential, and this is the variation in frequency per unit volt, and this is called electronic sensitivity. So you can calculate electronic sensitivity. So this is all about the two cavity klystron and reflex klystron. And the second device is magnetron. You know, in magnetron there are so many cavities. In reflex klystron, we are having one or two cavities, and electrons interact with few cavities, therefore efficiency is small. In magnetrons, we are having a large number of cavities. So by extending the interaction of RF field and electron beam, we can extract more and more power from in the magnetron. So this is the basic construction of magnetron. We are having a cylindrical anode with cavities, and there is a cylindrical cathode, and this is the DC power. The same concept is here. By accelerating the DC power, by applying the DC power, we accelerate the electrons, and this electron interact with the cavity. Now we use magnetic field to change the path of the electron. The electrons emitted from the cathode move in a curved path and then interact with this cavity, grids of these cavities. So this is the interaction. Suppose the cylindrical cavity is in this mode, means right plate is positive and left plate is negative, then this is called retarding interaction. At this instant, the electrons transfer their energy to the cavity, and this is the accelerating interaction. Means left plate is negative, right plate is positive, and electron extract energy from the cathode cavity. So by applying a certain fixed beam accelerating potential and a magnetic field which is perpendicular to the plane of the path of the electron beam, so that this electron move in a circular path or curved path. When this electron emitted from the cathode moving in a curved path passes near the grids of this cavity, then these electrons either interact in accelerating mode or retarding mode. If it is in retarding mode, then power is transferred to the cavity and then it move near to the cavity. If it is in accelerating mode, means energy is transferred from the cavity to the electrons, then the electrons move with high velocity and move towards the cathode. So slow electron move towards the anode, fast electrons move towards the cathode, and then again it is reflected by the cathode and then interact with next cavity and then transfer energy to the next cavity. If it is first electron transfer energy to the first cavity, then it's slowed down and then absorbed by the anode. If it is in the accelerating mode, means energy is absorbed by the cavity, then it moves towards the cathode and then reflect back and then interact with another cavity. So electron moving in a circular path continuously try to interact with the cavities till they transfer their energy to the cavity. Therefore, almost 90%, 80% electrons transfer their energy to these cavities, and these cavities are internet connected and we extract power from the cavity to the output circuit. So this is the basic means mechanism in the magnetrons. So thank you very much.
नमस्ते डॉक्टर सक्सेना।
नमस्ते।
थैंक यू सो मच, आपने अपना अच्छा खासा टाइम दिया और इतना डिटेल्स में सब चीज़ बहुत अच्छे से आपने समझाई। थैंक यू सो मच। ओवर टू एंकर्स बच्चों।
Now the session is ready for queries. If anyone has any query, you can ask. So sir gave a very informative and useful lecture, starting with very basic concept of amplifiers and oscillators. He explained limitation of these conventional solid-state active devices at microwave frequency. Sir also elaborated the working of two conventional microwave sources, cavity klystron and reflect klystron. So thank you so much, sir, for this very informative and wonderful lecture.
Thank you. It's my pleasure.
Thank you, sir.
Okay. Welcome.
Now heading towards the second session. For the second session, we have Dr. Summa Mukherjee sir. Mukherjee sir is currently working as assistant professor in the electrical engineering department at IIT Jodhpur. Sir is currently working on substrate integrated waveguide based antennas and circuits for microwave applications, and sir has specialization in microwave and communication engineering. Sir also received the International Travel Grant from the Department of Science and Technology, Government of India. He is also a recipient of the Young Scientist Award APRASC 2019, instituted by the International Union of Radio Science. And now I would like to invite Sir and request him to brief us on the topic basics of antenna measurement. Here you can go, sir.
Namaste, Dr. Mukherjee. Namaste, Dr. Mukherjee. This is Susha Bhatia, HOD Physics and convener of the workshop. Welcome to the workshop, and thank you for
Thank
sparing your valuable time. Please
thank you.
start your
Thank you.
deliberation.
Yes. So please tell me if my screen is visible. Is it visible to all?
Yes, audible and visible both.
Okay. Thank you. So very good afternoon to all of you. So today I'll discuss about the basics of the antenna measurement, and I work in the electrical engineering department at IIT Jodhpur, as it has been already mentioned. So this is my email ID. So whatever if you have any query after today's presentation, you can definitely contact me in my email ID. So this is the outline. First, I will very briefly discuss about the microwave networks, the scattering matrix basics. These are some basic things you need to know once you go for the measurement. I will very briefly touch about the measurement block diagrammatically, how exactly the microwave measurement is done, and then the basics of the vector network analyzer, and then I'll go to the antenna parameters and antenna measurement basics. So if I try to measure any microwave network, so basically we can very simplified form, we can think about a two-port network. And a typical two-port network looks like this. So it will have two connectors connected into a microwave circuit. This is based on a microstrip technology. There can be anything. It can be a waveguide, it can be anything else. So basically right now what we are looking after is not in between. Let's create a box, and there are two ports. Okay, and if we want to see the conventional transmission line model, which you probably have seen in your this classroom, that is what you have seen, right? That this is the network. So this is the transmission line, there is a load, there is a source. I think that I have also mentioned here, and this is your port 1 and this is your port 2, and this is what practically it will look like. So in between there will be something which right now we are not interested to know what is inside. We want to characterize this two-port network by some means. So if you all have gone through the basic circuit theory concept, you all have seen that we can characterize a two-port network by means of Z matrix or Y matrix. So typically that would look like this. Basically this is my two-port network, and this is the Z and Y matrix representation, right? But when it comes to microwave frequency, then there is a problem. The problem is where? So if you see, so what we do in the circuit theory, we don't know what is inside. We have this block, we want to characterize it, we connect the port 1 and port 2 with voltage source and current source, whichever we want to measure, whichever way we want to measure. And once we get those Z and Y matrix, we forget about what is inside and use those metrics to represent this circuit in our mathematical calculation. How it helps? It helps multiple times, because we don't need to think about very much physical phenomenon which is happening inside, because everything is reflected in this matrix. Directly you do calculation with the matrix, we know that the same thing will happen in this circuit, and that's how it becomes very easier. We don't even have to go into these details of the transmission line theory as well, if we can do that. Now where is the problem? The problem is that in transmission line theory, as you all have seen, is that we have incident and reflected voltage wave. So here there is a concept of the characteristic impedance because of the distributed circuit phenomenon. There is a concept of the impedance mismatch, which will create reflection of the incident voltage, which is not in the conventional circuit theory. Same is true for current. So therefore, anywhere you want to measure the voltage, that will be summation of incident voltage, that is V naught plus e to the power minus gamma z, as well as reflected voltage, which is V naught minus e to the power plus gamma z, right? So this creates a problem, because then at each point this summation of the incident and reflected voltage wave is changing, and as you can see, these are function of z, which was not considered here. Here, whenever we are trying to determine any network represented Z or Y matrix representation, at each point my voltage and current are constant. Not constant in the sense that it is maybe time varying, but it's not a function of position inside the circuit. Therefore, we could make a ratio and that ratio would represent the circuit, but that is not true here. As you can see, these are function of the Z. That means in between the circuit at different point, these ratios are going to change. So therefore my impedance is also going to change. Same is true for the admittance. So then people figured out, okay, fine, these are not constant, this summation is changing, but there are something which is constant. What is constant? Constant is the reflection coefficient, because that is only function of the load impedance and the characteristic impedance. Once it is fixed, we know that for this circuit this is constant. So if we can try to relate our matrix circuit representation in a matrix form from those quantities which are constant, then it will be much more helpful for the mathematical calculation. So from that concept actually came the S matrix representation. I am not sure whether how many of you have gone through this scattering matrix representation. S stands for scattering matrix. So what we typically do here is ratio of, instead of voltage and current, we are actually separating this incident voltage and reflected voltage and making a ratio of this, and that we are representing as a matrix which will represent this black box. Okay, because as I said, one example is that this ratio of the incident to reflected voltage wave, which is called reflection coefficient, I mean reflected voltage of incident voltage wave, so that is actually constant. It's only function of the load impedance and the characteristic impedance. So for a particular circuit it will become constant once you connect it to a load. So then we can try to interpret the circuit in a matrix form by this manner. So if we just go into, say, for two-port network, it will be just this four element: S11, S12, S21, S22. What is this definition of this each element? So the definition is like this: Sij will be Vi minus by Vj plus, provided Vk plus equal to 0 when k is not equal to j. What does it mean? So it is the ratio of the reflected voltage wave coming from the ith port to the incident voltage wave coming from the entering into the jth port, provided all other incident voltage wave at all other ports, k ports, are 0. And this condition is typically you can ensure if you have made matched termination, because matched termination means there will be nothing reflected back, so there is no as such positive voltage wave, that is the incident wave coming from that port. So this condition is very important, and if you make this condition, so you can actually extend this scenario by this. Okay, I'll come to that part later. That if you make this condition for two-port network, so if you make k equal to 2, V2 plus equal to 0, that means if you make this matched load, then your S11 actually is V1 minus by V1 plus, which by definition we know from the transmission line theory is the reflection coefficient. As I said, reflection coefficient is only depends on the load impedance and the characteristic impedance. Therefore, we are trying to relate the circuit behavior in terms of something which is constant throughout the line. So again, remember that only the magnitude of the reflection coefficient is constant. It is still a function of z. So there will be a, if you try to relate the phase, then there will be a problem. So we are right now only considering the magnitude. Okay, so if we now from the two-port network, if we want to extend it, it will look something like this, that arbitrary n-port network. So at each port there will be incident wave as well as reflected wave. Okay, and the matrix representation will look like something like this. Same definition. So it looks like this. Just like the previous slide, we had Z or Y matrix. Here we will have S matrix. Okay, now in the similar way, we can actually follow the logic for this kind of scenario. So for microwave circuit, we actually will try to measure this S matrix rather than Z or Y matrix. And from the circuit, microwave circuit concept, we can show that once we get this S matrix, we can convert this S matrix into a Z matrix or Y matrix. There are formulas for that. So the step is little bit elongated from the conventional circuit theory concept. In conventional circuit theory, you have a circuit, you represent it in terms of Z or Y matrix and treat it as a black box, and then you interpret that circuit in your mathematical calculation with the help of the Z and Y. Here we cannot directly measure Z and Y, but we can measure the S, and once we measure the S, we get the S matrix. We can convert the S matrix into Z or Y matrix, and then the procedure remains same. So after we convert the S matrix into Z matrix, we can actually try to calculate the behavior of the circuit in terms of Z or Y matrix. Okay, just like the conventional circuit. So that is the idea. If you do it pen and paper, typically people, what people do when it comes to measurement, they only mention about this S matrix. So they measure the S matrix by some instrument, and how that is done, that's what I am going to discuss today. Okay. So the simplest thing which we can think of about the measurement of the S matrix is called simple reflectometer. So basically what we are trying to do, our target is that this is my two-port network, this is port 1, this is port 2. A1 is the incident wave, incident wave in port 1, and B1 is the reflected wave in port 2. And similarly, A2 is the incident wave in port 2, and B1 is the reflected wave in port 1. A2 is the incident wave in port 2, and B2 is the reflected wave in port 2. So we want to measure these all quantities, A1, B1, A2, B2. Why? Because once we get those quantities, we can make the ratio and get the S matrix parameter. For example, S11 will be B1 by A1, S21 will be B2 by A1. Similarly, the S12 will be B1 by A2, and S22 will be B2 by A2. This is coming from this definition, Okay, so of course there will be this condition that this is matched. That means when I am measuring S11 equal to B1 by A1, we are assuming that there is a matched load connected at port 2. That's why the B2 is 0. Okay, similarly when B2 by A1, that means B1 is 0, because here we are ensuring that matched load condition. Okay, so that's how we can actually measure the S matrix, and how we can get this A1, B1, A2, B2. That's what I'm going to discuss now. That is the simple reflectometer concept. So if I see the block diagrammatically, this is how you can measure it. So our device under test is this one, this red box. This is a device which we want to measure. So basically we want to represent this device in terms of a two-port network whose S matrix will be known. So as I have shown in the earlier slide, basically we are trying to measure 4 parameters, S11, S12, S21, and S22. And typically for a reciprocal circuit, we only need to know S11 and S21, because other two will be just equal to those 2 parameters. So basically we are trying to measure 2 parameters, S11 and S21, right? How to do that? So this is the very simplest way you can try to think. So this is your device under test. As I said, that once we are trying to measure A1 and B1, we will make the port to matched load. So the other port is matched, okay, that you can see here. And let's say this rho f is the reflection coefficient which is coming from this here. So then something is reflected back, that ratio is the rho f. That means if your incident wave is A1, then the reflected wave will be rho f multiplied by A1. Okay. Then what are the other things? So we have sweeper. Sweeper means is a frequency sweep source. Then that is divided into 2 paths by a 3 dB splitter. So this is nothing but a power divider which is dividing this signal into 2 paths. One is going here and one is going here. The one which is going here is actually used as a reference, and the other one, first it went to attenuator. Why this attenuator is used, I am coming to that. Then there is a directional coupler. I hope you all have a little bit knowledge about the directional coupler, how it works. And then it is connected to the bandpass filter and matched load. So why this directional coupler is used, if you all know the principle of the directional coupler, you all know that whatever is reflected back, something will be coupled into this line, right? And that coupled one, we will feed it to the complex ratio meter. So this reflected one is B1, and incident, which is incident, that is here and here is same. So we know that that is A. So B by A will, in a complex ratio meter, will give us the value of the S1. That's the thing. Okay, we are utilizing this directional coupler coupling mechanism. We could have directly tried to do that, but then that will be a 3-port network, so it will create a problem. So by means of this directional coupler, we are ensuring that the original path is not disturbed. Only if we know the coupling of the directional coupler, the C value, then we know that how much less signal is going here, so that we can add up here, right? And then make the ratio. So we will get the actual S11 by this method. Okay, but there is a problem. The problem is the errors in the different instruments. That means there are multiple components. There is a component called 3 dB splitter. There is a component called directional coupler. All these components may have some error in between, and that will create a problem. How? So let's see. So this is what I was explaining. That is what is explained here, that matched load is connected, so A2 is 0. So S11 measured will be B1 by LA. Since we have used the attenuator, so LA will be multiplied. LD is the insertion loss of the directional coupler, multiplied by A1, which is coming into the path 2. Same is going in the path 3, because this is a equal splitting power divider. So whatever power is going here, the same power is going here. So they are equal in nature. That's what is the conventional block diagram. But if we have error, then what will happen? So let's say, very simplified condition we will think about, that we have only error in the 3 dB splitter. That means whatever path is wave is coming back, which is coupled through here, right? Something is reflected back, that is coming, and something is coupled of that into this B. But whatever is coming here, then ultimately it will reach here. And what if there is again a reflection coefficient due to the mismatch of the impedance? So we'll again have a path or wave which is going through this path again. So that scenario we have considered, that as if this 3 dB splitter is not perfect. So whatever wave is coming into this path, that will have a reflection coefficient of rho s. Okay, so what will happen if my incident wave is A? This path, it is going A by root 2. Why A by root 2? Because this is voltage over amplitude we are talking about. So this is an equal power splitter. That means both the path will have equal power. So voltage will be A by root 2. So A by root 2 it went through the attenuator, so LA multiplied by A by root 2. Then there is insertion loss LD, so LA LD A by root 2, and experienced a reflection. So rho f is the reflection coefficient. So the reflected voltage will be rho f LA LD A by root 2. Again, so whatever is coupled, it is coupled. So again the LD is coming, so rho f LA LD square A by root 2. Then it is going again to the attenuator, so LA square LD square A by root 2 into rho f, and it went to power divider. Now is the case where this reflection again is happening because of the imperfect power splitter. So rho s is the reflection coefficient. So we have another wave coming into the same path, rho s, rho f, LA square, LD square, A by root 2, and so on. Again here will be reflection, again it will come back, again here will be reflection, and infinite number of reflection will happen. In addition, we are also assuming that whatever wave is coming back to this point, some part of that is also transmitted into this reference path, and that coefficient is called K, transmission coefficient. So the path, the signal came rho f LA square LD square A by root 2 up to this point, that multiplied by K is actually transmitted here. So each time the infinite number of reflection is happening here and here, some of the components are going in this path. So whatever I discussed, I'll try to show it by arrow. So first wave is going, the red one, up to band pass filter, the device under test, experienced a reflection, came back up to power splitter. Okay, then we have two things. One is the reflection, that is multiplied by rho s is the reflection, and one is transmission to the reference path. So again, so that is gone, that component is gone, multiplied by k, and some part is actually reflected back to the same path, and this cycle will continue. So each time of this reflection is happening at this power splitter, we are adding one component in this path as well as we are adding one component in the reference path. So now if you try to calculate this measured reflection coefficient by the ratio of the B by A, since of these components are coming into the picture, your measured result will be something like this. So your B1 will be coming like this, which is a infinite series. So you can use that mathematical calculation of the infinite series, and similarly the A1 will also be an infinite series. So ratio of them, which was supposed to be this but will happen to be this, which is a function of this imperfect splitter rho s and k. You can see those things here. Okay, so there is a error in a simple reflectometer, because in practice, in practical world, nothing, not a single instrument you will find which is actually working perfectly fine. There will be some small error, and this small error can give you large deflection in your measured result, and that's where we have to correct those errors by predicting what is the source of the error, and that's where is the measurement of the microwave circuits becomes little bit complex. So all the microwave measurement instrument, why it is so costly? Because of this, because inside that instrument there is a computing system which is trying to predict these errors and trying to rectify it so that you get the accurate result, and this accuracy is actually paid off by the high cost. Okay, so if you want to see the error, that error function looks like this. This is very simplified form where we have not discussed that anything is reflected back at the attenuated part or the directional coupler part. If you added that up, then the function will be much more complex, right? Now, why this attenuator is used? Because we can see that there is multiple reflection into this path. That means once it is gone, again coming back, again gone, again coming back. So at each point, this attenuator will attenuate this amplitude of the wave. So after 2-3 cycle, the wave will be very much attenuated, and then there will be no more reflection. So just to ensure that this error is getting erased, we are actually adding a attenuator in the path. Okay, that was the purpose of the attenuator. So if you want to see the error function, that's what is the case, and if you see in magnitude and phase form, that's how complex it will look like. Ultimately, it is just a function of this k and rho s, which are the imperfect 3 dB splitter property. That will define that how much error we can get. This is only when you are trying to measure the S11, that is the reflection coefficient. What will happen for the transmission coefficient S21? So then the block diagrammatically the system will be little bit different. So it will look like this. So this is your source. This is 3 dB splitter. So one path is going here, and one is reference path, and then the ratio meter. So this is my device under test DUT. Okay. So rho 1 is the reflection coefficient at this point, and whatever is coming back, that will have a reflection coefficient rho 2. And we are also assuming that rho d is the reflection coefficient at detector. Okay, so now again here will be then multiple path and multiple reflection will happen here also. So we will similar way can calculate the what we should expect. And in addition to that, we can also try to calculate the imperfect 3 dB splitter, so it has a reflection coefficient rho s. Then what will happen? So if we want to predict that, we will try to get the two cases. One case is that one without DUT, so only reference signal. So that will be the case here. This is by the signal flow graph. I don't know whether you have the exposure of the signal flow graph concept. This same thing we are representing by a graph, so that is called signal flow graph. And the second case, with the addition of the device under test, it will look like this. And if you just solve the signal flow graph, the ratios will be like this. The first case is that without the device under test, the meter reading by the source will be this. And the second case is the device with the device under test, so rho 1 and rho 2 come into the picture, and T is the transmission coefficient. Actually, we are trying to measure T, but that is coming as a function of this M2 by ES with these all other terms. Rho S is the imperfect splitter, that is also coming into picture. All other rho 1, rho 2, rho D also coming into the picture. We are trying to measure only T, but directly we will not be able to find it. We have to solve these equations and find it. So ultimately, my measured Tm, which should be equal to T, will be actually a function like this, which is 1 minus rho S rho D, and this is the thing. So this rho S is coming into the picture. If it was not there, then it would be much more simplified, and we would have got the actual T instead of Tm. So this is the error, and this is what we have to rectify if we want to get the accurate result. So this is very basics of the any microwave circuit measurement, including the antenna measurement. That's why I just wanted to briefly introduce you that what is happening inside the measurement instrument. Okay, now these two system, this one is the only the reflection and one is the transmission. These two system, if you want to combine, then this two coupler reflectometer is the technique which you have to use. So here is the source. So whatever is going through to the DUT, that is also reference is taken by the coupler, one coupler, and whatever is reflected back, that is taken as the another coupler. So two coupler is there, but this all system will be actually based on a principle that its directivity is infinite. That means nothing is getting back between the isolated ports, but that's in practice that will not happen. Some portion of the signal will come back to the isolated port, and therefore the error will come into the picture. So I will not go into the detail of that. I will just show you different types of errors which happen in this system, and this is the system which we typically use in our daily life measurement system. Okay, so we have to take care of those errors. So typically 3 errors we get, and these are function of all this imperfect directivity. So you can see that directivity terms are coming in D1 and D2. These are coming. If they are infinite, then this would not have come. Okay, so these 3 error, magnitude and phase, we have to separately calculate, predict, and then whatever reading we are getting from that, these effects has to be taken care of, and then only we will get the accurate result. Okay, so this is just a brief idea. We will not go into the detail of that. So basic system is this, that we will use 2 directional coupler, and the coupled path will give us reference and the test, and ratio of these two should give us the measured S parameter. Once we get the S parameter, we can convert it into Z parameter, and once we get the Z parameter, the conventional circuit theory concept can be applied. This is the very basic of the any microwave circuit. Okay, now we will see what is the instrument. The instrument is called vector network analyzer. Looks like this. This is the old days instrument, and nowadays it looks like this. Okay, it has typically you will see 2 port, but it can be also 4 port. Even more than that also is possible. There are this type of products are there where multiple port VNA is also available, but typically that is costly. So most commonly, if you go into any microwave lab which has actually network analyzer, you will find this type of instrument. So how we actually measure? So this has two cables along with these two ports. You connect your device under test here with these two ports. So now this is just a two-port connection. One side is connected to source, other side is the load. Load is matched load. So then you can actually, again, you can follow the same procedure what I have discussed so far. That ratio of this reflector and incident voltage will give you the S matrix. So if you go inside to this vector network analyzer, basically this is what is you will find. So this is your device under test. Okay, and you see that there are two directional couplers, just as I said, the two directional coupler reflectometer technique. So one is used, whatever is incident wave that is sampled, one is used, whatever is reflected that will be sampled. So all the four component you will find by each part. So this part is actually the RF testing part. After that, it is only signal processing. How? First, it is actually by help of the mixer, it came down to a kilohertz range, because the microwave signal is came back to the kilohertz range. After that, it is converted into A to D converter, and then once it is converted into digital signal, we can do the computer processing and calculate the result. Okay, all these errors and all those things we can calculate here and display the actual result instead of whatever is getting recorded in the measured result. So all these things we can do here. So just to implement this digital processing purpose, we are actually using multi-stage mixer to convert this gigahertz range signal into a kilohertz range signal. And then we are doing the A to D conversion. But nowadays A to D converters are also getting advanced. So maybe in future we will have, instead of this big box, in fact actually nowadays also it is coming very small boxes, because A to D converter at higher frequencies are also coming into the picture. So this mixer part is getting obsolete, and then we can hold it in your pocket. I'll show you some of the example. So this is the very basic idea. The two directional coupler reflectometer is the basic measurement setup with additional processing. So that's why the cost is coming. So typically, if you are using a 20 gigahertz VNA, it's cost about 20 lakhs, more or less, something like that. Okay, so what I said is that there will be imperfections and we have to predict those imperfections. So what we need to do to predict those imperfections, that's what you need to know when you are going into a microwave lab. So that is called calibration. So there are multiple ways to calibrate. Most popular one what people use is the SOLT calibration, short open load through calibration. So typically if you go with a VNA, you will be given this type of devices. One is open, it is written on the that device. One is short, one is load, and one is through. So there will be male and female versions of these circuits. So male and female, by means of that, this hole, whatever you are seeing here, that will be different. In one case, the pin will be coming out, and one case there will be socket to hold the pin. So depending on your device is having which pin, that's how you have to select. If your device is having a connector which has a socket to hold the pin, then you have to use the male type of open short load through. If otherwise it is, then female you have to use. Okay, and what it typically does, so first it will connect the open, it will record what is the response, then short, then load in both the ports, and then through. Through means that from port 1 to port 2 they're connecting it and recording the result. So what it actually will do is that these are all standard load, we all know. Open means that ZL equal to infinity, and short means that ZL equal to 0. We all know what we should expect in a transmission line theory for this type of load. We know that what should be the reflection coefficient. Once we measure it and that is deviating from our theoretical value, we know that difference is the error. So we can calculate the error very precisely by using this well-known load. So that's how this load means that this is a matched load. That means it is 50 ohm if you are using a 50 ohm cable. So for that case also, we know that the reflection coefficient should be 0. If it is not happening 0, then the difference is the actually the error. So that's how we can very accurately predict the error, and that error we will use in that data we will be used in the computer processing to calculate to predict the actual value of the measured result. Okay. Similarly, the through connector is used to get the idea what is the additional phase in this path is happening because of the wave is traveling into this additional path instead of the DUT. So that phase is also getting calculated, and your measured result will show by subtracting this additional phase, so that you will get the accurate result. So this is how people do. So whenever you go to a lab, you want to measure with a VNA, you have to actually first do this calibration. In both the ports, you have to put first open, then short, then load. Here also port 2 also open, short, load, then connect the through, calculate all the values, then push the correction button. So it will automatically inside computer will calculate the errors, store it, then you start your measurement. So then you will get the actual result. So these are the old days, people were given this type of setup. Nowadays it is coming very compact way. So this is called eCalc kit. Everything is very computerized. You just connect it. It will also show in your screen that now connect this, now connect that. So very straightforward way people are doing nowadays. Getting more advanced, getting more user friendly. At the only the thing is that the price is increasing. That's it. So as I said, so nowadays the VNAs are also coming very pocket handling mode. So there are two types of VNAs you will find. One is very bulky in nature, which you have to put it in a table, as well as very small like this. So these are nowadays started to come very low cost, very low profile. Okay. Although not low cost in the sense that this is 20 lakhs, maybe this is coming around 3 lakhs. So that way it is very less costly, but still it's not like you can buy directly in your market, but you can actually. Nowadays it is coming, and as the advancing will go on, we will be able to see more compact form of VNA, and just like multimeter or something, probably one day we will be able to measure these things. So this is the what I said. So right side, left side is the compact one, but low cost, but low performance. The right side is the highest one, high cost and high performance. So this is USB based small VNA. Typically 1 lakh cost will be there. Whereas if you use a tabletop terahertz frequency VNA, it will be costing around 4 crore. So all the ranges are right now available in the market. Depending on your application, you can buy and measure any of them. Okay. So now with this knowledge, we can now come to the antenna concept, that how we measure the antenna. So the very basic circuit diagram you can see here, and the very basic setup you can see here. So this is your tabletop VNA. Antenna is a one port device, so only one port cable is connected to the antenna, and this is how we will try to measure the reflection coefficient coming from the antenna. Since it is a one port, so in the S matrix we will be only having S11. So I'll come to that. So before that, let's first discuss that what is this setup theoretically looks like. Theoretically, it looks like this. So this is my piece of transmission line. That is this black one. The source is connected at one end of the transmission line. That is this VNA, and load is my antenna. And if we want to represent this antenna in a circuit theory form, we have these two resistance and one reactance. That is the typical equivalent circuit for any antenna. So one is RR, which is radiation resistance. This RR is responsible for the radiation. So more value of RR means more radiation you can expect. RL is the loss resistance, which is the inside loss because of the conductor dielectric loss that you have to account for. XA is the reactive part, not contributing to the radiation, but it is unavoidable. So you have to model those effects here, and that's how the system will look like. Okay, and once you get this transmission line model, you can actually apply the theory of the transmission line, and you will definitely get the impedance mismatch because of the characteristic impedance will be Z0, and this will be input impedance will be function of RR, RL, and XA. So they will not match. So there will be a reflection coefficient, and that's what you can measure. Once you get S11, you can convert it into Z parameter, Zin. And once you get Zin, you can actually use it as a circuit theory concept. Same thing you can do. So what is happening physically? Physically, this is my source, and in the transmission line, the source is exciting the transmission line. So TEM wave is passing through the transmission line, and once it reaches to the antenna, this special form of the antenna is actually ensuring that this TEM based wave is actually exciting a plane wave in a free space, and then it gets radiated. So antenna radiation mechanism I will not be discussing here, essentially, that you can revise. So this is how it is happening physically, and the circuit theory wise, this is how it will represent. And we are actually doing this thing. Okay, and what to measure? So again, if I am coming back to the same system what I discussed at the very beginning, so suppose this is my antenna, we will try to use it as a circuit theory concept. So this is my port 1 where the source is connected, a piece of transmission line, and then antenna. Okay, this is my antenna. Okay, and then there is a transmission line, and then port 1 is connected to the source. So basically this is how it will look like, block diagrammatically. So basically the antenna we are trying to model as a black box with a one port connected only. This is a one port network. So instead of Z and Y matrix representation as similar case, we cannot do. We will have to go by S matrix representation because of the voltage and current wave reflection is coming, and S matrix representation is the same, but since it is only one port, so only S11 will be there. So only thing, instead of Sij, we will be having S11. And if we just make it very simplified, so this is my VNA, this is my antenna. So just remove the transmission line part, say then there is a generator and an antenna, and this is how the equivalent circuit will look like. So generator has voltage Vg, internal resistance Rg and Xg, and the antenna has the loss resistance RL, radiation resistance RR, and Xa is the reactive part. This is the circuit. And what we are calculating? We are calculating S11 because whatever current we are giving, there will be reflection because of the mismatch. So we will have reflected voltage wave and incident voltage wave. Ratio of that will give us the S11. By definition, since there is no port 2 here, so by definition, this is equal to the reflection coefficient tau n, which is actually Zin minus Z0 by Zin plus Z0. So with the help of the VNA, if we can calculate S11, we can actually calculate the Zin, which is RL plus RR plus JXA. So we actually get the equivalent resistance and reactance of the antenna. Once you get that, you can utilize the antenna as just a circuit parameter. So that's the target. And what we typically define when we measure the antenna, so this impedance information will actually be represented in terms of impedance versus frequency response. So we defined, since this Zin is actually a function of frequency, at different frequency, its value will be changing. So we will make a graph, and in that graph we can say that okay, this antenna is working very precisely into some band. What is the band? The band where its input impedance is matching to the left side impedance. Then that is the case where whatever voltage wave we are giving or current wave we are giving, that is getting accepted to the antenna, almost negligible amount is getting reflected. That is the frequency where this antenna is working. So that part we can fix from this graph. I'll show you an example and I'll show you what is exactly I'm talking about. So from there, actually, we'll be able to find out the impedance bandwidth of the antenna. Bandwidth, typically, if you go to buy any antenna, you will be asked that what is the bandwidth you want. So that's what we'll get it from here. Okay. So typically, antenna radiation mechanism looks like this. So if you excite an antenna, there will be current, oscillating current, and that oscillating current will create this voltage wave, as well as this voltage and oscillating current or voltage can create electric and magnetic field. Okay, and so what exactly you can measure? One thing is that in the input port you can measure the impedance, and then you can get the impedance bandwidth. For the radiation part, you have to actually measure the radiation pattern. So what is that? So basically this is how the radiation is happening. So what you can calculate is that at the far field, the electric and magnetic field. Okay, this is what at some particular point, position from the antenna, how the electric field and magnetic field at different position is varying. From there you will get a proper idea that how this antenna is radiating. For example, for this antenna, all the radiation is happening this side or this side, nothing on the top and bottom. So actually here and here we should get very less amount of radiation. So that you can actually measure at different location of theta and phi at some constant radius r from the antenna, and that will give you that idea that okay, this is where the radiation is happening and this is where the radiation is not happening, and that plot is called radiation pattern plot. Okay, so basically a dipole antenna will look like this. Then the radiation will happen something like this, spherically outward, and along the dipole, actually plus z or minus z, there will be no radiation. So radiation pattern will look like this, and there will be a color graph. I'll show you that. So typically this type of color graph, red is the maximum and blue is the minimum. So this color graph will tell us that okay, wherever there is red, there is the maximum radiation. Wherever there is no red, that means there is no radiation is happening. So if you see any typical radiation pattern, this is how it looks like in a 3D plot. And what does it tell? So you can see that one of the portion of the plot is very much bigger than the others. So basically it is telling that the antenna is radiating much more in this positive z direction, that means theta equal to 0 direction, and in all other direction there is very less amount of radiation. There are some other parameters also we try to discuss, like half power beam width. So this is the angular section within which most of the power is getting radiated. Basically this is the angular separation between the 2 points where the radiated power is half of the maximum. So maximum is here, half of them is here. So angular separation between them is the half power beam width. These are very important parameter, because this tells us that whether the antenna is focusing all its radiated energy into a small angular section, or it is very widely spreading its energy into multiple directions. Because typically our antenna measurement is targeted in a way that from one point to another point we want to actually send the signal wirelessly. So basically we don't want our antenna to radiate equally in all directions. We typically want it to be focused. So basically if you make it very concise angular section, that is what we require. So that how effectively it is doing it, the measurement of that is HPBW, half power beam width. Okay, so by measuring the radiation pattern you can actually get this information. Okay, so of course you also need to know the distance which you have to follow. So I hope you have very basic idea of the antenna radiation, that there is a near field region and the far field region, and also near field region can be bifurcated into reactive near field region and radiating near field region, and typically these are the boundary for these two regions. So basically you have to put your measurement setup into far field region, that is 2d square by lambda, where d is the maximum dimension of the largest dimension of the antenna and lambda is the operating wavelength. You need to keep at least this distance to measure the radiated field, because below that your field is radiating less, there will be a reactive power is there. That means this portion at this position, the fields which are coming out from the antenna is actually oscillating into the nature. So basically plus and minus r direction and plus and minus theta direction, it will be oscillating, and they will not radiate. The power is standing there stationary, it will not travel. After this distance only it will start traveling into free space. So you have to accurately measure here, not here. Why? So that you can see here, suppose this is my antenna. If you are very close to the antenna, if you try to measure with respect to different theta, this is how it will look like. Now once you start going out of the antenna in the outward r direction, you will see slowly this pattern is changing. So in the radiating near field region, there will be some variation, but still it is very less, and also at different r distance. That means suppose you measure here, you measure here, and you measure here, this pattern is keep on changing. So depending on which position from the antenna, what is the distance inside this region, your variation of the radiated power in different theta direction will be different. But if you go into the far field, then it is fixed. Once you reach this far field region, this variation with respect to the theta and phi, that means this position, this position, this position, this position, and at different R distance, that means here, this all will be same. All will be having same variation. So we are actually measuring, we have to measure here, because we actually work with the antenna in this region only. Never put the two antennas into very close to each other, because that will not work. Okay, so that this part is shown here. If you see here, this is the radiation pattern plot in a 2D scale. So this is from theta equal to 0 to theta equal to 4 pi, and you see that the three distance, one is 2D square by lambda, one is 4D square by lambda, one is r equal to infinity. And you see in all cases the shape remains same. Only thing is changing is the null. The null value is changing. Rest of the things remain same. That's what I said. At this far field, every position will give you the same radiation pattern, and that's why you have to measure here, not in between. Okay, so this is about the basic things. And then this concept of the major lobe, which is the lobe containing the maximum radiation, and side by side lobes are called side lobe. These are also some important parameter. You need to know that how much is the difference between the major lobe and the side lobe, that people typically say. Back lobe and minor lobes, these are the different parts of the radiation pattern. I hope you will have at least one course on antenna engineering, so there you will be able to see all these details. And also there is a concept of principal E-plane and H-plane pattern. So basically principal E-plane pattern is the pattern which contains the direction of the maximum radiation as well as the direction of the electric field. And principal H-plane pattern will be direction of the maximum radiation and the direction of the magnetic field. For example, if you take this horn antenna, which is having kind of similar type of field distribution of waveguide, so in this case the dominant TE10 mode will be having the H field along the y-axis and E field along the z-axis. So if this is the radiation pattern, so the principal E plane will be ZX plane, whereas principal H plane will be XY plane. So why this is important? Because 3D radiation pattern, constructing them into a plain paper is very difficult to do. So what people typically do is that they actually make it a cut into 2D plane. So which of the 2D plane you need to cut? So typically people do what? They do principal E plane pattern and principal H plane pattern. That means where the electric field direction is there and where the magnetic field direction is there. These are the two cuts what people typically do when they want to represent the radiation pattern into 2D plane. That's the basic concept. Another thing is polarization. You also need to think about what polarization this antenna is radiating. So it can be a linear polarization, just like the one you are seeing. It can be a circular polarization. That means you see that here that this arrow is moving in circular fashion. Okay, the field can be like this. So if your antenna is radiating in circular polarization and you are trying to measure that antenna with a linear polarized antenna, your result will be not accurate. So you have to actually see that whether which circular polarization it is, and that circular polarization antenna you have to use for measurement. Then only you will get the actual result. Similarly, it can be also elliptical polarization. So I'm not going into the detail of this polarization part. I'll show briefly that how the measurement setup will look like based on this. So this is the concept of the polarization loss factor, that if your polarization is not matching, so for example, suppose your antenna is directed in this horizontal polarization and your measurement antenna is around vertical polarization, your receive power will be 0. So this alignment of polarization is very important, otherwise you will not receive any power. So at different position you will get 0, so you will think that there is no radiation is happening. That's not the case. The case is that polarization is different, that's why you are not receiving the power. That you need to consider. So basically, if you have a cross dipole configuration which is actually radiating in circular polarization, So one will be horizontal polarization, one will be vertical polarization. Both the component will be there. And if you are trying to measure it with a linear polarized antenna, you will actually catch one of the polarization. The other polarization you will not be able to catch, and therefore the received power will be less. So whatever you will calculation will be actually with only one component you are doing, so it will be very less in nature. So that's the wrong thing you will find out. Okay, so whatever I discussed, I'll try to show you with an example. Suppose this is one antenna which I designed long back. So I'll just show you that how it looks like all the parameters. So the first thing I'll show is the impedance bandwidth. So I discussed this part, right? That it is connected to the generator. So just like this one, this is the VNA connected with the cable with an antenna. So this is my source. This is my equivalent circuit of the antenna, and we should be able to calculate the Zin as a function of frequency. So as I have discussed that we typically calculate S11. S11 is also a function of Zin. So once we get the response of the S11, we can actually convert it into Zin, and then we can get the information. So here at the left side, what we are showing is S11 in dB scale and as a function of frequency. Okay, so you see this type of graph you can see. So here actually two graphs you are seeing. One is simulated, that is using a simulation software, and red one is actually the measured by the VNA. Okay, and they are matching almost in all position, you can see. So this is actually saying that at this point and this point the antenna is working properly. Other point, it is close to 0. So S11 dB scale close to 0 means it is actually either open circuit or short circuit, and the less it is, that means it is very much close to the impedance matched condition, and that's the frequency where this antenna is operating. So typically the bandwidth is measured with the scale of -10 dB. So this is the limit. So the F1 and F2 within this band limit is called the bandwidth of the antenna. So for this antenna it is very narrow in the two bands, but this is a dual frequency antenna. That's how we can get this information from this graph. Next is the radiation pattern. So simulated radiation pattern looks like this, but how to measure? If we want to measure at each point and try to find out those nulls, it will be very tedious job to do and very time consuming to do. Actually, we don't need so many information. So what we will do, we will make the principal plane cut. So one cut will be ZY and one cut will be ZX. So that you can see here. This same radiation pattern cut in ZY will look like this in the 2D scale. Same radiation pattern cut in the ZX plane will look like this in the 2D scale. So antenna engineers need to understand from these two 2D curves that what the radiation pattern typically will look like in a 3D plane. And from there they can predict that what is happening. So from here you can see that at theta equal to 0 and with the half power beamwidth of this much, maybe around +20 to -20, it is radiating. Whereas here it is 0, but the half power beamwidth is much wider, maybe +90 to -90 it is radiating. So in one plane it is very wide, in one plane it is very narrow, and that's what you are getting here, right? Very small, but in this case very wide. So that is how the radiation is happening. It is the antenna is radiating in a something like the very small angular section in one plane, but very wider angular section in other plane. That's how the most of the power is radiating from this antenna. And as you can see that this is the side lobe level, okay, and similarly all other lobes, whatever you are seeing here and here, they are the minor lobes. Okay. Okay, so this is about the radiation pattern. Then the next thing comes is the gain. So typically for gain measurement, you will need two antenna. One will be your reference antenna and one will be your test antenna. You can connect one of them with the transmitter, other one is the receiver or detector. So typically in the lab you will find like this, but remember the distance between the two antenna must be far field, otherwise your measurement will be wrong. And typically we actually use the freeze formula. So here I have mentioned both the generalized one as well as the conventional one, and this is what we typically use. So if we know gain of one antenna, we can measure the gain of the other antenna from this formula, because we know the distance between them, we know the operating wavelength, we can calculate the PT and PR. So PT is known because it is transmitted, and in the receiver we detect what is PR, the received power, ratio of them, and we putting the value of lambda and R. If we know one G0T, we can find out G01, and that's how we can calculate the gain of the antenna. So basically you need to know a reference antenna whose gain is known. Then you can actually measure the gain of the other antenna. That's how the measurement is done. Okay, so these are all about the basic theory. Now what is, I'll very briefly show you what is actually is done. So the drawback is that if you try to do it in the open space, is that this distance, which is far field to be used, sometimes this antenna is so large that it becomes very much difficult to do in a actual open space. Then there will be reflection from the surroundings that will that also come to this antenna. For example, here we are actually assuming that whatever is radiating, that is only coming here. But if there is a reflector here and here and here, that will also reflect something, and that will also come to here. So whatever you are measuring at the receiver, that may not be only due to this, maybe reflection due to this also. So that is another issue. Similar like things are there, multiple issues can be there. So there are multiple solutions for that. The two solutions I am showing here. One is the reflection range, where one wave is coming from here and one wave is reflected from the earth ground. So this is how it will model. One image source will be created, and that's how we can calculate. Basically there is a two wave is coming, one is reference and one is from the reflected. So they will be strongest enough rather than the reflection from the other cases, and that's how we can neglect the other reflections, and whatever is measured we can predict that okay, this is what is happening. Other thing is that we are trying to simulate the condition what we theoretically did, that no reflection from the other cases will be there. We can design a room which will simulate this condition, that whatever is reflection from the others, they will be minimized, and we will ultimately create a plane wave incidence into the antenna. This plane wave is important because in the far field we are only considering theoretically that the antenna is incident with a plane wave. So we have to create this plane wave. So in the reflection range, we have to have sufficient distance so that this plane wave happens, which is the far field. But for different antennas, this size may be very big, so we cannot do that. If we want to do it in a room, then we have to design the room such that this plane wave is happening, and that is typically is called free space range. Most commonly this is what is used, and there is multiple techniques to do that. One is the compact range, where we actually use a reflector. So your antenna is here, it is radiating, this reflector is creating a plane wave instead of a spherical wave, and then plane wave is coming to the test antenna, and then we measure through the detector what is the detection value, and that's how we accurately can measure the same thing in a small enclosed chamber instead of a big large area required as far the calculation is concerned. So this is very commonly used. I will show you some of the figures. So basically block diagram looks like this, the same as I have shown in the freeze formula calculation. Test antenna is connected with the this receiver, the source antenna is connected with the source, and then there is a controller for height and position, distance between the antenna. Everything is getting recorded, automated, and then you will get the accurate result. So more automation you feel here, more accurate result you will get. Okay, so these are the block diagrammatically for different combination. For example, there can be a single frequency, only at a single frequency you can measure. There can be a swept signal where multiple frequency you can measure simultaneously this gain. So all these things are there, but the basic block diagram remains same. Only additional components you have to add. Okay, so this is the calculation just coming from the freeze formula. You know G0T, you know R, you know lambda, you have recorded PR and PT, you can calculate J0R. That's it. That's very straightforward. So how it actually looks like? So actually it will look like this. This type of room is called anechoic chamber. So what is this? These things, these are called absorber. What it is used for? So like I said, we actually don't want reflection from different sections. So these are used to absorb those incident electromagnetic waves so that nothing is reflected. Only wave incident to this test antenna is from the reference antenna. And to ensure that, you have to cover the room with this, and that's why this system is very costly. Maybe 50 lakhs or 1 crore is required from that. I think in Jaipur, some of these systems are available. You can visit there and see it. So it can be, depending on what type of antenna you are measuring, it can be small, like a small room like this. It can be as large like this, where you can actually enter a vehicle, and vehicle mounted antenna also you can measure. Okay, even an aeroplane as large as this. This is the human and this is the antenna, and you see that this type of reflectors are used to ensure that the reflection is coming with a plane wave, as well as small chamber of a room size like this. The same system, big as this, as small as this. Both the things are possible. Depending on your antenna size, the size of the room will be bigger or smaller. And this is how the absorber looks like. So basically, it are all different materials, specified materials used just to ensure that all the incident wave is absorbed and nothing is getting reflected. Yeah, so that's where I conclude that I have covered some of the basics, and as you can see that there are multiple ways to measure it. The basic concept remains same, but depending on how much accuracy you want, you actually need to choose your instrument. So you can actually try to measure the antenna parameters in an open lab, but then there will be some error. You can try to minimize them by using computation. But if you want to actually do accurate measurement, then you have to use very high cost setup. So lastly, I will just very briefly show you some of the things of our institute. So this is the administrative building. We are here. This is the Jodhpur Blue City. I think most of you will probably know. And this is established in 2008. We currently have around 200 faculty members and around 2,700 students. Our department is having MTech in SIoT and CPS, and PhD in different domain, including microwave. We in microwave, we are having regularly different project positions. So if you are interested, you can definitely contact us, and multiple positions are typically available with us. So thank you. Thank you all for listening to us. Thank you.
It was an excellent presentation. Dr. Thank you so much. I must say, not only the participants, even I learned a lot. Thank you so much.
Thank you. Thank you.
If anyone want to any question, he or she can ask from sir. If anyone is having any query, he or she can ask from sir. Okay. Sir, it was a very informative lecture. We have learned a lot about the most important components of antenna, starting with the basic, also about various antenna parameters, its reflection coefficient, directivity, radiation patterns with 3D effects shown through images. So I take this opportunity to thank you on behalf of the institute and students who were captivated by your talk. Thank you, sir.
Thank you. Thank you very much for inviting me.
It's a pleasure, sir.
Thank you, Rajiv.
I think one has raised hand. Is there any query? I saw one raised hand. I don't know whose name it is. Probably some mistake. Okay, thank you.
So you are also invited in validity ceremony.
Yeah, it is starting now.
Yes, sir.
Okay.
Now we will have validity of this 2-day workshop. A very warm welcome to all of you to the valedictory ceremony of hands-on training in microwave experiments.
In these 2-day national workshops, we have had deep insights of several subjects of microwave experiments. We focused on what are microwave, remote sensing fundamentals and applications. We learned how different microwave components work, also about measurement of dielectric constant and waveguide components, and we had a very lively session.
And now, heading towards the ceremony, I would like to invite our Honorable Vice Principal Ma'am, Dr. Rajna Saxena, for the welcome address of valedictory ceremony.
I feel privileged to address on behalf of Kanodia College. I take this opportunity to welcome each one of you to the valedictory function of the 2 days hands-on workshop on microwave experiments. I very gratefully acknowledge the presence of our eminent guests who have joined us this afternoon. It is indeed our pleasure to have amongst us Dr. Parul Patel as chief guest of today's function and Dr. S.N. Joshi as guest of honor. I extend a very warm welcome to both of you. Welcome, ma'am. Welcome, sir. Your graceful presence is indeed a source of motivation for all of us, and we look forward to your knowledgeable address. I compliment the organizers of the workshop for the efforts they have put in. I am confident that the workshop has definitely enhanced the knowledge about microwave of all the participants, as we have had very good technical deliberations since yesterday and are eagerly looking forward to the valedictory session by our learned and experienced guests. Thank you.
Thank you, ma'am. Now, for the report presentation, I would like to call Dr. Sumita Shekhawat, ma'am.
Good afternoon, one and all present over here. Today's National Workshop and Hands-on Training in Microwave Experiments was organized on virtual platform using Google Meet by Department of Physics on February 18-19, 2022 with a view to motivate young participants to look forward for their future prospects in the field of microwave electronics. The participants were exposed to various theoretical and experimental aspects of microwave circuits, antennas, as well as their applications, with an aim to provide a forum for young minds to learn about the fundamentals of microwave components and measurements. In this 2 days workshop, there were 6 oral sessions in all, 4 sessions on the first day and 2 on the second day, by the invited speakers from various renowned universities and research institutes. Each session was followed by an interactive question and answer session where the students clarified about their doubts and also interacted with guest speakers. A total of around 250 participants from various educational institutes registered themselves in this workshop from all over India, even overseas too. The event started with the welcome speech by Principal of the college, Dr. Seema Agarwal. She welcomed all the delegates, participants, and students connected to the workshop virtually. She emphasized on experiential learning as college promotes it for the overall development of the students. She congratulated and wished good luck to the Department of Physics for conducting such kind of quality workshop, having various sessions by distinguished speakers. Dr. Sarla Sharma elaborated the theme of the workshop. She highlighted the important aspects which were to be discussed in the workshop. She also gave a brief description about the objectives of the workshop as to make the students aware about various career opportunities and to know about it in depth. Professor Deepak Bhatnagar, former head, Department of Physics, University of Rajasthan, as guest of honor of the inaugural ceremony, encouraged the young participants of the workshop to use this virtual platform as an opportunity to interact with the eminent speakers from all over country to understand the basics of experiments as regular classes are not taking place due to COVID-19. In this reference, Professor said that such kind of workshop is a big need of present scenario. The chief guest of inaugural and the keynote address was Dr. Surendra Pal, Additional Director ISRO. In his address, highlighted that research canvas is going vast in the present scenario in the field of microwave electronics. He stated microwave is like a god because of mobile, TV, 3G, 4G, 5G technology, as God is everywhere. He motivated participants to think out of the box as you cannot exist in the present time without it. With growing technology now, we have simulations through which things can be elaborated in depth in various areas like submarines, water communications, etc. He introduced about the journey of radio communication by various researchers like J.C. Bose, pioneer in the field of microwave devices and known as one of the fathers of radio science. James Clerk Maxwell, who discovered electromagnetic equations, Oliver Heveside, who reformulated Maxwell's equation, which is also known as modern Maxwell equations. He concluded the inaugural address by the convergence and fusion of various technologies like broadband, satellite links, video conferencing, GPS, DVS 300 channels, etc. He further explained about the fundamentals of antennas and its importance. He demonstrated various kinds of antennas such as dichroic antenna which works on X-band, omnidirectional antennas for floating system, KU band, microstrip antennas, tapered dielectric antennas, etc. Dr. Sumita Shekhar delivered general thanks to Chief Guest Dr. Surendra Pal and Guest of Honor Dr. Deepak Bhatnagar for such an encouraging and motivating lecture. Professor Deepak Bhatnagar was the speaker for the second session. In his talk, he discussed about the basics of microwave components with live demonstration, starting from the fundamentals of microwaves like its frequency range, various frequency bands. He also explained about the microwave components which are used in microwave bands in laboratory like Klystron tube, Klystron power supply, isolator, attenuator, frequency meter, detector, and point contact diode, along with the explaining the working of each of these components. The third session included the talk of Dr. Parul Patel, Group Director, SAC ISRO, in her talk on microwave remote sensing, fundamentals and application. She explained about the common bands used in microwave remote sensing, elaborating the concept of polarization. She discussed satellite microwave radiometer used in Bhaskara 1 and Bhaskara 2, MSMR, multi-frequency scanning microwave radiometer. She presented a deep analysis of soil moisture profile map using SMAP surface SMC data, where SMAP is first Earth observation satellite developed by NASA, which was launched in January 2015 and work on L-band. She spoke about scatterometer, satellite altimetry, Doppler radar, ground penetrating radar, which is used to detect the signal beneath the surface. The fourth session, which was the last session of the day, was led by Dr. Manisha Gupta. She is presently working as an associate professor in Department Physics, University of Rajasthan. She delivered her talk on measurement of dielectric constant and waveguide components. She explained about the various parameters of waveguide T's like isolation, coupling coefficient, etc. Explaining about the fundamentals of directional coupler, she elaborated about the measurement of various parameters of directional coupler and parameters to define performance of directional coupler. Professor Viren Saxena was the speaker for the first session of day 2. He is presently working as professor in Department of Physics, University of Rajasthan. In the talk, he discussed about the vacuum tube type conventional microwave sources, starting with very basic concept of amplifier and oscillators. He explained limitations of these conventional solid state active devices at microwave frequencies. Sir elaborated the working of two conventional microwave sources, two-cavity klystron and reflex klystron. In continuation to this, he also explained the basic characteristics of reflex klystron with the help of experimental data and results. The second session included the talk of Dr. Somba Mukherjee from IIT Jodhpur. Sir discussed most important component of communication, that is antenna, and its measurement basics. Sir has started with microwave network basics, followed by scattering matrix basics. Sir also explained simple reflectometer principle and reflection coefficient measurement instrument VNA, vector network analyzer. Sir elaborated antennas working and its parameters like gain, directivity, radiation pattern. Sir very interestingly explained using experimental approach about the basics of antenna measurement. All the sessions jointly form a complete package to understand basic microwave technology. Now we are towards the end of the workshop, a formal valedictory program in which we will listen to our honorable chief guest, Dr. Parul Patel. Our guest of honor, Dr. S.N. Joshi, could not join us due to some unavoidable reason. I will end with the hope that we will again meet in the very near future. Thank you, everyone. Over to our anchors now.
Thank you, ma'am. Now, I would like to introduce our today's guest of honor, Dr. S.N. Joshi, sir. Sir did his MSc Tech in Electronics and Radio Engineering from Allahabad. He has also been in SERI for last 45 years and presently holding the post of Emeritus Scientist at SERI. Sir has coordinated the activities of microwave engineering. He has also been the chairman of various advisory community of different organizations like ISRO, DRDO, DAE, CSI, and BHU. So due to some unavoidable reasons, sir won't be able to join us, but we are still lucky to receive his blessings.
Now, I consider it a great honor to welcome our today's chief guest, Dr. Parul Patel, ma'am. I think you all remember ma'am from yesterday's session. Still, I go for a little intro from the vast. Dr. Parul Patel, ma'am, is a senior scientist with Space Application Center, ISRO, Ahmedabad. At present, ma'am is Group Director, Research, Training and Outreach Coordination Group, SAC, PhD Guide at Nirma University, Ahmedabad. So now I will request ma'am to enlighten students with her wise words. Here you go, ma'am.
Thank you. Very warm welcome to all of you to this valedictory session. In fact, it has been great sessions. I could see Dr. Usha Bhatia, Professor, in fact, your Dr. Seema Agarwal, the principal herself, has taken keen interest that can be seen in the way whole program has been formulated, the topics which are selected. Dr. Seema Agarwal, Dr. Usha Bhatia, in fact, Dr. Shushma, who has been coordinating with us. I see Dr. Deepak here. I could, in fact, listen to some of his yesterday when the discussions were going on. So I was really impressed the way, with the zeal, the details which were explained. The true faculty flavor we could see when he was explaining on the board like that. I could not participate in the other sessions, but the topic itself, I could see that right from understanding the dielectric constant, the basic interactions which are happening, the waveguide components, and all the micro basics, like if you have to utilize the microwaves for the benefit, then you have entire that micro experiments, each aspect of experiment has been covered. As I mentioned, right, dielectric constant, like I see dielectric waveguide components, the antennas which are there, in fact for micro sources. So you are talking about the vacuum tubes also. So students have got all the entire end-to-end, I would say, microelectronics or antenna, everything, it is encompassing every aspect of microwave. In fact, I try to show that yes, once you have all these micro in place, the sensors are in place, then how do you make use of it? So right from, students can choose in future, like in which direction their interests are. So that way, this workshop I found is something which is very much welcome, and in spite of all the pandemic and all the restrictions that we have today. Now, of course, we are hoping that yes, the situation will be better and we'll be able to interact in person, and actually, have some hands-on also during some workshops, this kind of workshops in future, near future maybe. Yeah, but this was really satisfying, I would say, looking at the kind of participants. In fact, right now also I see more than some 50 participants in this valedictory session also. So that shows that yes, the kind of talks and the kind of invited talks and this you have organized, and the enthusiasm that is there in the workshop participants, and you have motivated the participants that way. So I wish all the best for all our participants in particular, and really I would like to have good interaction with the speakers, the eminent speakers that you have had, like from some of our retired ISRO scientists to Professor from Siri Pilani, Dr. Joshi, who everybody knows that the kind of contribution that is there, and the professors who are there from your physics, your Jaipur University. So that was really heartening, and I really look forward to interacting with all of you, the faculty of this Kanaria PG Mahila Mahavidyalaya, and all the eminent speakers in future. And all the best. Thank you.
Thank you so much, Dr. Parul, for your inspiring words. We are honored to have you in the workshop. But I would just like to tell you something. Since Professor Bhatnagar is very much here, actually microwaves are everywhere, and I don't know why people say microwave electronics is not physics. It's very much physics. And since we use microwaves daily in our lives, and moreover, it's a part of the curriculum of our PG students also. So keeping that in mind, we simply planned for this workshop, and the planning was actually we were holding the this workshop. We planned to take the support of Professor Bhatnagar. We could only plan because Professor Bhatnagar is in this field and he is a very good friend of mine, और मुझे पूरा भरोसा था कि वो हमें मदद पूरी करेंगे. एक्चुअली हमारे पास इतने रिसोर्सेज नहीं थे, बट हमने प्लानिंग करने की हिम्मत इसलिए दिखाई बिकॉज प्रोफेसर भटनागर वाज वेरी मच विद अस, एंड माय सिंसियर ग्रैटिट्यूड टू प्रोफेसर भटनागर. उन्हीं की वजह से हम इसको इतना सक्सेसफुली आप सबसे हम कांटेक्ट कर पाए, and this was organized very well, and the number of participants, it crossed almost 250 from all over the country, and even we got overseas participants. If I speak about the success of the workshop, though I am not very happy regarding the participants. जब हम इतने एमिनेंट स्पीकर्स को बुलाते हैं, उनका इतनी एनर्जी, उनका टाइम हम लेते हैं, तो मुझे अफसोस होता है कि पार्टिसिपेंट्स, आपने नंबर बताया, फाइन, द नंबर इज गुड, और मैं आपको बताना चाहूँगी कि यूट्यूब हमारा लाइव स्ट्रीमिंग चल रहा था और उसमें भी बहुत सारे पार्टिसिपेंट्स जुड़े हुए थे. सो फाइन, द नंबर इज परफेक्टली ओके, बट एक्चुअली उनका प्रेजेंस ज़्यादा होना चाहिए था, तो ताकि वो आप सबका इतना टाइम हमने लिया, इतनी एनर्जी हमने ली, तो कम से कम वो वेस्ट नहीं जाना चाहिए था. तो मैं आई सिंपली वांट टू रिक्वेस्ट ऑल द पार्टिसिपेंट्स कि कम से कम आगे के लिए थोड़ा सा कोशिश करें. एज का कोई मतलब नहीं है, हम लोग इस एज में आकर सब एक दूसरे से सीखते हैं, और जब भी किसी एमिनेंट स्पीकर को सुनते हैं तो कुछ ना कुछ नई बात तो हमको भी मिल जाती है। ऐसा तो नहीं है कि एवरीवन हैज बिकम मास्टर ऑफ द सब्जेक्ट। तो कोई बुराई नहीं होती है जिंदगी में नई चीज सीखने की, हम ये नहीं मान के चले कि हमें सब कुछ आता है। तो दैट इज माय सिंसियर रिक्वेस्ट टू ऑल द पार्टिसिपेंट्स, and I am very much thankful to the honorable speakers, Dr. Parul, Dr. Deepak Bhatnagar, Dr. Surendra Pal, जिन्होंने अपना इतना valuable time हमारे लिए निकाला. Thank you so much, everyone, and my again special thanks to Professor Deepak Bhatnagar. Thank you so much, Deepak ji. Over to anchors.
Thank you, Parul ma'am. It was such a great pleasure to hear you and have you in this workshop.
Now I would like to call Anshul Bharadwaj for feedback. Anshul Bharadwaj.
Yep. Greeting of all the day to each present here, to all my respected sirs and madams. My name is Anshul Bhardwaj and I am a student of the Agarwal PG College, MSc final year in Jaipur. I found this workshop a really helpful, one of the most enjoyable and informative workshop I have ever attended. This workshops not only helpful for our exams but also for the in real life as well as. This completes our almost syllabus of the fourth paper of microwaves, and I would like to thank the Dr. Surendra Pal sir who gave the basic and advanced knowledge of the microwaves. The basic microwave components were cleared by Professor Deepak Bhatnagar sir. His presentation it made the looks all the concepts easy, understandable, and very understandable to all the students. Also would appreciate the information shared by Dr. Parul Patel on the microwave remote sensing topic, and Dr. Manisha Gupta ma'am share her knowledge on the measurement of dielectric concept and waveguide components, which we have the experiment practical in our laboratory also. To give the lecture, I would like to thank the Professor Virender sir and the Soumya Mukherjee sir to give the lecture on the vacuum tube type conventional microwave sources and basic of antenna measurements, which give the complete information of the antennas measurement, which are the knowledge of the antenna, the measurements, which is the working and the limitations we have covered. Is all of in it's easy and understandable for all the students we are here. At last, I would thank you all the organizers for such wonderful workshops for organizing and give the opportunity to participate in it. And after that, particularly, I would like to thank my HOD ma'am, Minal Bafna, or the HOD of the Agarwal PG College, who give a chance to share this information and motivates us all of this. And we would urge such workshops would be held in the futures to increase our knowledge. Thank you.
Thank you, Anshul.
We are very curious to know what are your takeaways from this workshop. We were successful in delivering what we planned for you. Is this workshop has been beneficial for you or not? So here is an announcement. So I request everyone to fill the feedback form. Unless you will not be able to fill the feedback form, you will not be able to get participation certificate. So it's my humble request to every participant to fill the form. We would also love to hear your valuable suggestions from our upcoming events. Thank you.
I would like to.
Yes, sir.
Usha ji, will you permit me?
Sure, why not?
It was really a wonderful workshop. You organized, the team of Kanodia College has organized this event very nicely, and I'm very thankful to Parul Madam for her gracious presence. Actually, I know Dr. Pal for a very long time. When I joined my PhD work from Malviya Regional Engineering College, Jaipur. and I joined on a Respond program that was given to my mentor, Dr. Rajkumar Gupta ji, and he was the person, Dr. Pal was the person who was associated from that time with our team. And till date, we are in very close contact. And two of scientists, Dr. Kamaljeet and Dr. V.V. Srinivasan, did their PhD under my supervision. So I am very much associated with ISRO, and I would like, because you are now also become a close in.
अभी रुक जाएगी तो तेरा क्या कर दिया इसने कुछ भेज दिया
Please mute your mic.
I will request you to please support the fraternity of this college in whatever way you can. Sumita is doing her research activity in microwaves, and still she also did PhD under my supervision, and now she is continuing. I'm having a very good lab in the university, and the faculty members of this college are using the facilities available there. So as I have now retired from the active service, and but I will request you to please support in whatever way the fraternity of this college. And really, your presentation was excellent presentation about remote sensing. I heard almost 50%, more than 50% of your session, because I was having an urgent meeting, so I could not attend the entire session. But that was a wonderful session, particularly for the students who are now understanding microwaves and remote sensing. Thank you, Parul Madam. Thank you, Ushaji. Thank you, Sumita, for uh, permitting me to talk something about the event.
Thank you, Professor Deepak Bhatnagar. In fact, Kawaljit, I remember she had, they had to be there with our some TDP programs also, they were involved. So they used to come and meet, and we had good work done with CD and this also. So that way really is, like our interactions with academia is always very fruitful. And we want to see that, yes, Indian academia, they contribute to the state of the art our programs which are there, and with the change policies, and the whole entire scenario is changing. So I'm sure that your valuable guidance to a lot of startups and all that will always be like needed. The times are changing with our in space and NCL in place. So we are like always relevant in this field who are contributed. So I'm sure your contributions will be useful to the country as such. Yes.
Thank you. Thank you very much.
feedback form has been linked in the chat box. You can fill it from there. Yes. Okay, now we are on the last step of this workshop. So here I will call Dr. Manisha ma'am for vote of thanks.
Good afternoon, all. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. Today, I feel honored and privileged to get the opportunity to propose the vote of thanks to all who have helped us in making this workshop such a resounding success. My first and foremost thanks go to all the participants from all over the country, even overseas, too, for their enthusiastic participation in this workshop. Thank you all. As you all know, organizing a workshop is generally the result of close cooperation among several institutions, organizations, and individuals. I, on behalf of the organizing committee, convey my deep regards for the support and encouragement provided by such individuals, organizations, and institutions. It has been our pleasure to host all the eminent scientists, researchers, students, guests of the workshop at Kanodia PG Mahila Mahavidyalaya, Jaipur for the 2-day national workshop and hands-on training in microwave experiment, HTME 2022. I would like to propose hearty vote of thanks to our chief guest for the inaugural program, Dr. Surendra Pal, former additional director, distinguished scientist, Satellite Center, ISRO, to grace our event by his presence. Thank you for your thought-provoking address. And our special and sincere thanks to Dr. Parul Patel, Group Director, Research Outreach and Training Coordinator Group, SAC ISRO, for taking her precious time out and consenting to be a chief guest for the validatory session and also be the invited speaker on the first day of the workshop. Ma'am, indeed your words have inspired all the participants. I would like to express our profuse thanks to Professor Deepak Bhatnagar, former head Department of Physics, University of Rajasthan, guest of honor for the inaugural ceremony and invited speaker for the second session of on the first day of the workshop, who despite his busy schedule has found time to grace his occasion and for sharing his valuable contribution. I wish to express our deep regards and sincere thanks to Dr. S.N. Joshi, Amateur Scientist Siri Pilani, to be a guest of honor for the validatory session for his valuable guidance. Thank you so much, sir. I express my deep gratitude and thanks to all the honorable invited speakers, Professor B.K. Saxena, Dr. Manisha Gupta, and Dr. Soumya Mukherjee for sharing their knowledge, finding and opinions in a very lucid way among all the participants with their excellent presentation and making this workshop interesting and meaningful. I wish to express our hearty thanks to Director Dr. Rashmi Chaturvedi, Principal Dr. Seema Agrawal, and Vice Principal Dr. Ratna Saxena, Dr. Sarla Sharma, and Dr. Diptima Shukla, and Dean Infrastructure Dr. Ranjula Jain for their perfect logistic support, guidance, and advices, which have greatly helped towards the successful organization of this national workshop. An event of this dimension cannot happen overnight. The wheels started rolling months in advance. We have been fortunate enough to be backed up by a team of very dedicated and motivated faculty members as the members of localizing organizing committee, non-teaching and lab staff, students and volunteers. I cannot thank everyone enough for the involvement they have shown and willingness they have expressed to take on the completion of the task beyond their comfort zones. My sincere thanks to the print and electronic media for their presence and giving excellent coverage of the workshop. I must say that this workshop is a joint effort of all. At the end, I would like to say that if time is money, then today you all have spent millions for us. Thanks to all of you for making this event successful. Thank you. Thank you so much.
Hello, ma'am. I fill up the feedback thing, but
So,
I have missed you the
so we are here to wrap up the workshop. So all the participants, speakers, and
Anchors,
are
just a moment.
requested to turn on your cameras for a group photograph. It was a request. Please turn on your cameras for a group photograph. Feeling gratitude and not expressing it is like wrapping a present and not giving it. So we all feel an immense gratitude for the organizers, the eminent speakers and participants. Thank you everyone for making it happen. A goodbye to everyone until next time.
Our president, Dr. Seema Agrawal, has sent a message apologizing that she couldn't attend the valedictory session, though she wanted to attend, but due to some reasons, she couldn't attend. So she is apologizing for that. Thank you so much, Deepak ji. Thank you so much, Dr. Parul Patel.
Thank
We'd
you.
like to see you again.
Thank you, Professor Bhatia. Thank you. Thanks to Professor.
Thank you, madam.
Thank you.
Thank you, Parul ji. Thank you so much.
Thank you. Thank you for inviting me.
Thank you, sir.
Thank you, Dr. Mukherjee. Thank you so much.
Thank you. Thank you.
I think Vicky Saxena was also there for some time. I don't know whether he is still there or not.
I think she just left.
Okay.
And Deepakji, once again, thank you so much.
Thank you very much, madam. Thank you very much.
Thank you.
So now I'm also leaving.
Yeah.
गारंटी नहीं है, बाकी मैं बता रही हूँ, ये लो।
तेरी गारंटी तो अपने आप में गारंटी है।
नहीं सर,